Hi guys, in this video I cover breadth first search tree traversal algorithm. There are two main traversal algorithms, depth first search and breadth first search. In this video I only focus on breadth first search. If you're curious about depth first search, please check out one of my other videos on that. I put a link in the description below. Breadth first search visits nodes level by level. It starts out with the root node at the very first level. Then it visits the root node's children at the next level, 2, 13, 45, 31, and then the following level, 76, 39, 83. And finally the last level with 11, 4, 23, and 18. Breadth first search accomplishes this by using the queue data structure. Essentially, the algorithm is exactly the same as pre-ordered depth first search. Let's see how this works. Initially, I have a queue, the queue is empty, and I enqueue the root node 7. Then, as long as the queue is not empty, I dequeue the front node and I enqueue its children. So I take 7 out and enqueue 2, 13, 45, and 31. 2, 13, 45, and 31 are the child nodes of 7. Then the queue is not empty, I dequeue 2. And at the same step, I enqueue 76 and 39, which are the child nodes of 2. Then queue is not empty, I dequeue 13. 13 doesn't have any child nodes, so nothing gets enqueued. Then I take 45 out of the queue. 45 has a single child node, 83, which is enqueued. Then the queue is not empty, I take 31 out of the queue. 31 doesn't have any child nodes, so I dequeue 76. 76 doesn't have any child nodes either, so then I move on, I dequeue 39. 39 has 11 as a child node, which gets added to the queue. Queue is not empty, I take 83 out of the queue, and 83 has 3 child nodes that get enqueued, 4, 23, and 18. Now I take 11 out of the queue. 11 does not have any child nodes. Then I take 4 out of the queue, 23, and 18. Now the order that I got by using a queue is exactly breadth first search. We can see I outputted 7, 2, 13, 45, and 31. And then 76, 39, 83. 76, 39, 83. And finally 11, 4, 23, and 18. 11, 4, 23, and 18. So by using a queue initialized to the root node, and then as long as the queue is not empty, taking a node out of the queue and enqueuing its children, we get the visitation order of breadth first search. Let's see how this is implemented. Now, for the implementation, I use a data structure where a node has 2 pointers. It has a pointer to the very first child node, and it has a pointer to its sibling. The dashed lines here is just the conceptual tree. The black lines are the pointers. So the root node does not have any siblings, but it does have a pointer to its very first child, which is 2. 2 points to its child, 76, and it points to its sibling, 13. 13 does not point to a child, but it points to its sibling, 45. 45 points to its child, 83, and it points to its sibling, 31, and so on. So keep this data structure in mind when looking at the code. In the code, I initially have a queue of node pointers. So those are pointers that point to a node. And the queue initially is empty. Then I enqueue the root node, 7, and then I repeat as long as the size of the queue is not 0. And as long as the queue is not empty, I take the node from the front of the queue and I remove it. So this would be 7 in the first iteration. Then I output 7, and then I push 7's children onto the queue. So here I have 7 in the queue, I remove 7, and I push the children 2, 13, 45, 31 into the queue. This works by taking the pointer to the very first child, which would be 2. 2 is not null, so I enqueue 2, then I go to the sibling. So sibling would be 13. 13 is not null, I push 13 into the queue. Then I get the sibling of 13, which is 45. 45 is not null, I push 45 into the queue, get the sibling of 45, which is 31. 31 is not null, and I push 31 into the queue. And when I then get the sibling of 31, this would be null. So null does not match the condition. The loop ends, and I check the queue size again. The queue size is not 0, so I take the front of the queue, which is 2, and I output 2, and I push the children of 2 into the queue, which is 76 and 39. So here again, I output 2. I get the first child, 76. 76 is not null. I push 76 into the queue. And then I get the sibling of 76, which is 39. 39 is not null. I push 39 into the queue, get the sibling of 39, which is null. This stops the loop. And then I go again, check that the loop is not empty. I get the front of the queue, which is 13. Remove it from the queue and output 13. Get the child node of 13. Now if you look here, the child node does not have any, 13 does not have any child nodes. So this one is null. I skip it. Check that the queue is not empty. Take the front of the queue, which is 45. Remove it from the queue and output it. And then get the child node of 45, which is 83. 83 is not null. I enqueue 83. Get the sibling of 83. Does not have a sibling, so it's null. This one does not match the condition, so it stops the loop. Checks again that the queue is not empty. Takes the front of the queue, 31. Removes 31 from the queue. Outputs 31. Gets the child node of 31. Doesn't have a child node, so it skips the loop. Queue is not empty, so takes 76, removes it from the queue, output 76. 76 doesn't have any child nodes, so the child would be null. So it skips the loop. Size is not 0. Takes the front of the queue, 39. Removes it from the queue, outputs 39. And then enqueues the child nodes, which is 11. And when it goes to the next sibling of 11, this is null, it would end the loop. So you can see by using a queue and then continuously removing the node at the front of the queue and enqueuing the children, which is done in this loop. This results in the visitation order or traversal order of breadth first search. 7, 2, 13, 45, and 31, 2, 13, 45, and 31, and then 76, 39, and so on. I hope you enjoyed this video. Thank you for watching.